Close your eyes. Let the stars gather gently behind them. Tonight, we are not staying on Earth. Tonight, we drift beyond the moon's old hush, past the familiar pull of our sun, and into the quiet where other worlds circle in silence. They are not fantasy. They are not far. They are real, and they are waiting. Some are scorched, some frozen, some wrapped in blue. Some may breathe, some may dream. In this soft journey, we float across the galaxy, looking for echoes of home, not to conquer, not to escape, just to wonder, just to sleep. This is the lullaby of exoplanets, the forgotten Earths we've never touched. The possibilities that blink in and out of darkness like fireflies too shy to speak. Breathe in, we're leaving the solar system. Breathe out, let your thoughts orbit elsewhere. Asterisk, you begin this journey not on a telescope mountaintop or a spaceship in flight, but in a quiet room lit mostly by screens and possibility. It's 1995, not long ago, yet far enough that the sky was still assumed to be mostly stars and silence. People had dreamed of other worlds. Of course, science fiction had lived in them for decades, but no one had seen one. Not really, not definitively. The planets we knew all belonged to our own sun, orbiting politely in a clockwork ballet, distant but graspable, studied by probes and patience. Beyond that, there was speculation, imagination, but no proof. No planet until a star blinked barely and the universe whispered back. It happened in the constellation of Pegasus. A star called 51 Pegasi, ordinary and yellow, like our sun, flickered ever so slightly. But the flicker wasn't what mattered. It was the wobble. The star moved, not much, just a gentle tug, like a dance partner stepping backward. It wasn't spinning wrong, it was being pulled. Something was orbiting it. Something big. Astronomers Michel Mayer and Didier Queloz saw the data curve and felt something inside them curved with it. It wasn't noise, it was rhythm. A planet, tugging on its star, invisible but undeniable. This planet would be called 51 Pegasi. BB, 'cause planets get letters, not names, at least at first. No epic title, just a designation. But what it represented was monumental. A planet beyond our solar system. An exoplanet. You let yourself drift now, quietly, through that early detection. The method was called radial velocity. It didn't look for planets directly. That was still too difficult, too much starlight in the way. Instead, it watched the star itself, looking for a rhythmic sway caused by a planet's gravity, like seeing a person's coat tugged from behind, but never seeing the hand that pulls it. The star was being dragged in a tiny circle. Something unseen was moving it. What they found wasn't a small Earth-like world. It was massive, half the size of Jupiter, but orbiting incredibly close to its star, far too close. The kind of orbit that would bake a planet, melt its clouds, whip winds into chaos. No one had expected a gas giant there, that close, that hot. We hadn't imagined that kind of planet could even exist. But there it was, a hot Jupiter, a term that would soon become common in exoplanet science, but was once unthinkable. And with that wobble, everything changed. You drift now through what came next. One planet turned into 2, then 5, then dozens. The sky cracked open and planets poured out. Most were strange, far stranger than anything in our solar system. There were giant planets with orbits shorter than Mercury's, planets that spun around to stars, worlds that should not have formed where they did. But the lesson was clear. Planets were common, not the exception, the rule. Almost every star, it turned out, had something orbiting it. The universe wasn't just a gallery of stars, was a sea of worlds. Imagine that feeling, lying under the night sky, knowing every dot of light above you might be orbited by a world. Not just might, probably is. Hundreds of billions of them in our galaxy alone. You're not just looking at stars anymore. You're looking at systems, possibilities, and you, tiny in your bed, are part of one such system. You are not the center of the cosmos, but you are embedded in its unfolding. But let's return for a moment to that first world. 51 Pegasi, Bayet, orbits its star once every 4 Earth days. For days to complete a year, it is so close to its sun that it is tidally locked, one side always in light, the other forever in darkness. Its skies would glow with unbearable heat. Clouds, if any remain, would be made of vaporized metals. It is not a world for walking, or resting, or dreaming. And yet, it is the first. It reminds us that discovery is not about finding something like ourselves. It is about expanding what we believe is possible. And it also reminds us that the universe doesn't have to cater to our expectations. It offers what it has, not what we hope for. After the discovery, a flood of telescopes began to watch the stars more carefully. Ground-based observatories were joined by space-based ones. Each brought clearer vision, steadier tools, and new methods. Radio Veloso was joined by transit photometry, watching a star's brightness dip when a planet crosses in front of it. Suddenly, we weren't just inferring planets. We were seeing their shadows, seeing their atmospheres, reading their chemistry. The sky was becoming readable, not just beautiful. And still, it began with a wobble, a nearly imperceptible tug, a heartbeat of movement where stillness had been assumed. You begin to feel how small signs hold vast truths. A flicker, a vibration, a small shift in rhythm, and suddenly, reality reorients itself. What was empty is full. What was imagined is now observed. You drift now alongside those early exoplanet hunters. Their joy was quiet, restrained by the rigor of science, but in their eyes was wonder, undeniable and awake. They knew what this meant, that we were not confined to our 9-planet sate, as it turned out, that there were other paths, other cradles, other chances. Life may still be rare, but places where it could happen, they are everywhere. And maybe that's what makes this discovery so quietly radical. Not that we found another Earth, we didn't, but that we found something unexpected, and then found out that the unexpected was common. That the universe is not only stranger than we imagined, but more generous. Night. The star 51 Pegasi still shines in the constellation of the Winged Horse. Its planet still circles, hot and fast and unseen to your eye. But now you know it's there, and that knowing shifts something inside you. It hums in your chest like a secret kept by the stars. There are more worlds than you will ever visit, more stories than you will ever read. But just knowing they exist, that they orbit, spin, glow, and breathe brings you closer to the cosmos. You don't need to travel to be changed. You only need to understand, and as you close your eyes, feeling your own planet spinning gently under you, another thought begins to drift softly forward. The one will follow in the next chapter, if we can't see these worlds directly. How exactly do we find them? Asterisk, you lie back again beneath the black bowl of sky, but this time you know something you didn't before. Most of what is out there can't be seen. Not with eyes, not with glass, not even with the biggest mirrors we've made, the planets, the exoplanets, do not send out light the way stars do. They do not burn, they do not blaze. They orbit, they reflect, they pass in silence. They are shadows moving through shadows. But somehow we find them. How? Not with direct sight, but with inference, with listening, with watching, with waiting. The universe is like a still lake, and if you watch long enough, you'll see the ripples, you'll feel the pull. You'll know something moved, even if you can't yet name it. You begin with the transit method. Imagine looking at a star, a small circle of distant fire, and watching its light. Not once, not twice, but again and again, night after night, year after year. Now imagine seeing that light dip ever so slightly, just for a few hours. Then it returns. The dip is shallow, like a breath held and released. And then, after a fixed number of days, it happens again. Another dip, and again, and again. Each time, the same depth, the same rhythm. It means something is passing between that star and us. Something blocking the light, just a sliver, just a moment. A planet. You've never seen the planet directly, but you've seen its effect. Like a moth flitting past a street lamp, you never catch its wings, but you feel the flicker in the glow. And with enough of these flickers, we can build a map. Asterisk, from the depth of the dip, we estimate the planet's size. From the timing, we know its orbit. From the length of the shadow, we estimate how fast it moves. And from these pale clues, a world takes shape in the dark. A world that was invisible becomes real. Now. Drifts slightly sideways into another method, the radial velocity technique, which feels less like watching and more like listening. Here, we don't look at the planet, we watch its star, and we notice something. The star moves. Not much, just a little sway, a tiny circular wobble. Why? Because the planet is pulling on it. Gravity is mutual. The planet doesn't just orbit the star orbits the planet too, just a little. Just enough to shift its light. And so, we measure the star's light with exquisite care. If it moves toward us, the light shifts blue. If it moves away, the light stretches red. This is the Doppler effect, the same phenomenon that changes the pitch of a siren as it passes. You on the street. But out here, the shift is not a sound, it's a color, a whisper in wavelength. And if that shift repeats blue, red, then we know something is circling it, something heavy, something real. These methods, transit and radial velocity, are how we found our first 1,000 exoplanets, each one a confirmation that the sky is not empty, that other orbits exist, that stars, like our sun, carry their own families. But those aren't the only ways. You drift again, this time into the subtle art of astrometry. Here, we try to map the position of a star over time with such precision that even the slightest wobble gives it away. It's like watching a candle flicker on a windowsill and knowing a hand brushed the curtain 2 rooms away. It's delicate, rare, but powerful when it works. Other methods come and go, like dreams, gravitational microlensing, where a massive object warps the light behind it, momentarily brightening a distant star and revealing a hidden planet. Direct imaging, rare but growing, where we block the star's light with a coronagraph and try to see the planet's faint glow directly, especially in young systems where planets are still hot from their formation. Even timing variations, watching pulsars or eclipsing binaries for tiny shifts in rhythm caused by orbiting companions. Each technique is a kind of listening. None see planets directly, not the way your eyes see a leaf or a flame, but they see enough to know what's there. You begin to feel the poetry in this, the idea that even what's hidden leaves a mark, that presence always leaves traces, that the universe can be read like a story written in shadows and sways in starlight. Think of this: you are lying in your bed, but the movement of a distant world light years awaken still reach you, through a telescope's lens, through a dip in brightness, through the shift of a spectral line, through a whisper in wavelength. You are connected to it, not by rope or beam, but by observation, by curiosity, by care. And slowly the map grows. One world becomes 10, then hundreds, then thousands. We catalogue them like seashells, not for their value, but for their variety. Some orbit binary stars and live in a sunrise that never ends. Some are frozen giants far from warmth. Some orbit so close to their stars they glow with molten winds. And some, just a few, orbit in the quiet zone we call habitable, not too hot, not too cold, just right for water to flow. We call that the Goldilocks zone, and it's where the dreams gather. But we haven't seen them, not truly. We've only read the signs, and isn't that how most deep things are known? Not through sight, but through evidence, through listening, through rhythm, through the way something shifts the space around it. You drift now toward Kepler, the telescope that changed everything. We'll spend more time with it later, but for now, know this: it watched one patch of sky for 4 years, never blinking. It didn't scan, it didn't sweep, it stared patiently, and in that stillness, it caught thousands of dips, thousands of planets, and it did so not with noise, but with silence. And that's the secret, isn't it? Finding a planet you can't see is not about technology alone. It's about knowing how to listen, how to wait, how to believe that even in the dark something moves, and you, floating in your quiet room, begin to feel like a planet finder yourself. You are not rushing, you are noticing. You are watching the people in your life, the world outside your window, the stars above you, and you are sensing things that don't speak loudly. Small tugs, small rhythms, a presence not yet seen, but deeply known. As your breath slows, as your mind settles into sleep, you hold onto that quiet truth. Not all things must be seen to be real. Not all stories must shout to be heard, and not all planets need light to be found. Some are waiting in the shadows, and in the next chapter, we will meet some of them, the strangest ones, the giants too close to their suns, the gas worlds that shouldn't exist, the wild, swirling orbits of the hot Jupiter. Asterisk, there is a kind of silence that comes not from absence, but from awe. And it is that silence that wraps around you now as we float closer to one of the strangest truths the universe has whispered to us. Some of the biggest planets orbit closest to their suns. Not small rocky bodies, not burning embers like Mercury, but giants swollen, gaseous, and fast. They should not be there, and yet they are. Welcome to the world of hot Jupiters. Close your eyes and try to imagine it. A planet many times the size of Earth, made not of rock but gas, circling its star not in decades or even years, but in days. Sometimes just a single day. That's one full orbit, one complete year. A loop so tight it brushes the edge of the star's breath. These planets are not drifting gently. They are racing, hurled by gravity, seared by light, torched by proximity. You might think, at first, of Jupiter in our own system, massive, cold, distant. It guards the outer regions of our solar neighborhood, like a giant asleep in deep orbit, too far to feel the sun's real heat. But hot Jupiters are nothing like this. They are pulled close, bound tightly. Their skies are scorched, their days are blistered, and their very existence confused scientists the moment we first saw them. You remember 51 Pegasi be that first exoplanet we discovered. It was a hot Jupiter, a gas giant where no gas giant was supposed to be, according to everything we thought we knew. Giant planets formed far from their stars, where it's cold enough for gas to condense, for icy cores to grow. But here was a giant so near its sun that it completed a year in less than for Earth days. It made no sense. It wasn't supposed to exist, and yet the wobble of its star was undeniable. The pattern repeated, the math held, it was real. More followed, dozens, then hundreds. Some so close they were nearly brushing their stars. Some so large they were puffed up by the heat, bloated like balloons, their atmospheres swollen by radiation. Some with orbits tilted or backwards. There was nothing orderly about them, nothing serene. These were worlds in crisis, worlds in motion, worlds forged in instability. You float now beside one. Let's imagine it together. The planet is about the size of Jupiter, maybe bigger. It circles its star in 3 days. The star itself is not so different from our sun, yellow, burning, ordinary from a distance. But the closeness changes everything. The planet is tidally locked, which means one side always faces the star, roasting forever, while the other side never sees light, locked in a kind of eternal night. The temperatures on the day side soar past 1,000 degrees Celsius. Clouds, if they exist, are made of iron vapor. Winds scream across the atmosphere at thousands of kilometers per hour, trying to mix the heat and cold, but never quite succeeding. It rains glass sideways. The air is a storm. The sky is metal, and yet it floats, obedient to gravity, spiraling endlessly around its sun. You wonder, how did it get here? The prevailing theory is that hot Jupiters don't form close to their stars. They migrate. Borne farther out, like our own Jupiter, they are nudged inward by the gravity of the gas disk that surrounds a young star. Or perhaps they interact with a sibling planet like dancers, colliding, and one is flung inward, caught in a death spiral that stops just short of the star's surface. These are not peaceful migrations. These are chaotic, violent moves. The systems that create hot Jupiters are not like ours. They are unruly, and the planets that survive, those that don't fall into the star, remain behind as molten monuments to their own resilience. Some hot Jupiters are even larger than physics should allow. The heat from the star inflates their atmospheres until they swell into puffed-up forms, light for their size, like gas-filled pillows wobbling in space. We call them puffy planets. Others are dense and compact. Some flare off mass as they orbit, leaving trails of gas like planetary comets. Some are losing their atmospheres entirely, stripped bare over time. They are not comfortable worlds. You would not walk there. You would not breathe. But that is not the point. They are not Earths. They are not homes. They are reminders that the universe is not designed for us. It exists beyond our preferences. But the lesson they offer is larger than heat or wind or size. It is a lesson in expectation. When we began looking for planets, we expected to find versions of our own. Rocky bodies, near stars, giants far out, neat, familiar, predictable. But the first planets we found did not obey those rules. They laughed at our order. They challenged our theories. They reminded us that our model of the universe was just that, a model, a simplification, a first draft, and in rewriting it, we made it richer. Now, scientists no longer assume that every system looks like ours. We know that stars are more creative than we imagined, that gravity is a sculptor, but not a tidy one, that chaos breeds variety, and that somewhere out there, in all the hot orbits and the wild swirls, might be systems where calm does exist, where Earth-like planets orbit gentle stars at patient distances. But we had to pass through the storm first, through the hot Jupiters, through the sun-scorched giants that burned away our assumptions. And there is something strangely comforting in that, in knowing that science does not flinch when it's wrong, that it listens, that it changes, that a single strange planet, hot, massive, misplaced, can teach us to see anew. So you lie back now, letting these giants drift past your mind's eye. You imagine their red glow, their high winds, their constant dance with heat. You feel the weight of gravity and the lightness of gas, and you rest in the idea that the universe is wilder than we imagined, but not hostile, not cruel, just wide, just full, just unfolding. You don't need to visit these worlds to know them. You know them already, in the part of you that understands change, in the part of you that has wandered close to the heat and stayed intact, and now, with the sky warm behind your eyes and the giants retreating into silence, you drift toward a quieter question, one that hums like a pulse at the center of it all. If some planets are too hot, what makes a world just right? And so, in the next chapter, we float gently into the quiet band around each star, the Goldilocks zone, where the light is soft enough, the distance kind, and the possibility of life begins to shimmer. Chapter 4, The Goldilocks Question begins. Now, ... there is a band around every star, a soft and silent ribbon, where the light neither scorches nor fades. It has no glow of its own, no color to mark its presence, but it is as real as gravity. Astronomers call it the habitable zone. Dreamers call it the Goldilocks zone. You are floating through it now. This is the gentle region where temperatures allow for liquid water, not frozen into silence, not boiled into steam, but fluid, free, able to flow and gather and cradle the fragile architecture of life. Earth sits inside this zone. So do the whispers of possibility around other stars. It's not a guarantee of life, not even a hint of it, but it's a beginning, a range, a question, and you're here to listen for answers. Imagine yourself orbiting a star not too far, not too near. The light is steady, warm but not fierce. The ground beneath your feet, if there is ground, hums with the chemistry of chance. Carbon bonds, hydrogen size, water trickles, puddles, dances. This is where the conditions are right, not perfect, not certain, but possible. The Goldilocks metaphor holds because of its calm. Too hot and water boils away oceans, become vapor, atmospheres drift off into space, molecules scatter, too cold, and water freezes locked in ice, chemistry slows, reactions halt. But in between, for a narrow band of space, warmth lingers without burning, pressure holds without collapse, and time can stretch long enough for life to try. Our Earth is a masterclass in this balance, spinning gently around a star that burns, bright enough but not too fiercely, with an atmosphere thick enough to hold in heat but not so dense that it chokes, at a distance where seasons bloom instead of perish. But Earth is only one version. There could be others. The habitable zone isn't fixed. It changes with the star. A small, cool red dwarf has a tight little zone, snug and close in, where planets must huddle near to catch enough light. A large, hot star pushes its habitable zone outward wide and distant, but often short-lived. The bigger the star, the shorter its life. And life, as we know it, takes time. Time to form, time to evolve, time to gaze up and wonder. So the most promising Goldilocks zones often belong to small, quiet stars. Red dwarfs glowing softly for billions upon billions of years. They are not grand, they flare sometimes, but they persist, and around them the slow simmer of habitability unfolds. You drift now past the star-trappist one. It's faint and red and only slightly larger than Jupiter, but it hosts a family of 7 rocky planets, 3 of them in the habitable zone. Scientists don't know yet if those planets hold air or oceans or warmth, but they orbit in the right places. They dip in and out of their stars, glow like children near a fire, and that is enough to stir the question. Kepler-186f is another. Slightly larger than Earth, it orbits a dim star in the constellation Cygnus. We've never seen its surface, but we know its distance, its size, its potential. It lies in the quiet gold ring, where temperatures might let rivers run and skies curl with clouds. It's a guess, yes, but an educated one. The Goldilocks zone is not a promise. A planet in that zone could still be barren, toxic, or stripped of air. Mars is in the sun's habitable zone and yet it's cold, thinnered, quiet. Venus is too and yet it is a furnace. A world's distance matters, but so does its atmosphere, its history, its geology, its magnetic shield, its chance. But still, the zone is where we begin. It is a sieve for our search. We cannot yet study every planet in detail, but we can look first to those in the zone, those with the right light, the right size, the right rhythm, and perhaps one day we'll find the right one. But what does right even mean? That question floats beside you now. Right for life, or right for us? We are carbon-based, water-loving, temperature-sensitive beings. We evolved in a particular cradle, and we carry that cradle inside our assumptions. But what if life elsewhere found another way? What if ammonia replaced water? What if silicon danced instead of carbon? What if intelligence bloomed not in skin and neurons, but in vapor, or magnetism, or crystalline patterns? The Goldilocks zone is based on us. It is a mirror of our needs. It is where we might survive. But maybe, in the long scroll of the universe, life has written other stories. Still, we search here first, because we must begin where we understand. We look for warmth, we look for balance, we look for a sky that might hold clouds, a surface that might shimmer with seas, a world that might hold quiet, growing things. And we know now that there are many. The Kepler mission alone found hundreds of candidates in the zone. The TESS telescope continues the search. The James Webb Space Telescope peeks into their atmospheres, searching for biosignatures molecules like oxygen, methane, carbon dioxide in just the right mix. Clues that something on the surface might be breathing. You drift now between these worlds, some too dry, some too stormy, some cracked, molten, or frozen. But a few, just a few, might hold what we dream of. And that dream is soft, not loud. It is not conquest. It is curiosity. It is kinship. You don't need these planets to be Earth. You don't need them to speak or wave. You just need to know they exist. That the conditions, somewhere, are right. That the cosmos makes room for more than one cradle. And maybe that's the most soothing thought of all. Not that we are alone. Not that we are not. But that the universe gives us options. That it draws a ring around each star and says, here, try here. Maybe something beautiful will grow. You exhale now, slowly. The stars keep spinning. The planets keep circling. And the Goldilocks zones keep whispering their quiet invitation. Not too hot. Not too cold. Just right. And as your thoughts begin to dim, another question begins to glow. If so many planets may hold life, what might that life actually look like? In the next chapter, we tiptoe closer to that question, not with certainty, but with wonder. We look at the ingredients for life, and we ask the cosmos, gently, what does it take for a planet to breathe? In the beginning, there was not life, but light, not breath, but fusion. Hydrogen becoming helium, helium becoming carbon, carbon becoming everything. The stars were the first chefs, and their kitchens burned not with gas, but with gravity. You float now through that ancient warmth, watching as the universe begins to stir itself into something more. You already carry the recipe inside you, in every cell, in every breath. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. 6 elements, familiar as dirt, invisible as air. But together they write the alphabet of life. They form the chains of DNA, the folds of proteins, the from of metabolism. They are not rare. They are not exotic. They are, in fact, astonishingly common. Which is why the dream of life does not feel so far-fetched. Let's begin with carbon, the backbone of everything that breathes. Carbon is like a clever hand with 4 fingers, always ready to link with others. It forms chains, rings, spirals. It's versatile, flexible, curious. That's why it's perfect for life. It doesn't just exist, it bonds. And in those bonds, complexity arises. Organic molecules are carbon-based, not because carbon is the only option, but because it's the best at building now. Add hydrogen, the smallest, simplest atom. A single proton with 1 electron. It's the most abundant element in the universe, born in the first seconds after the Big Bang. It floats, drifts, joins. It's in your water, your breath, your blood. Combine it with oxygen, and you get water, H2O. Solvent of life. Liquid water is the great connector, dissolving molecules, carrying nutrients, allowing reactions to unfold gently. It cushions, it cradles. It creates space for things to grow. Oxygen comes next. A fiery element, born in the bellies of stars. It binds to hydrogen, to carbon, to everything. It powers combustion and respiration. On Earth, it turned our skies blue and let creatures grow large. It's not required for all life, but for the kind we know, it gives breath. Nitrogen, phosphorus, sulfur, they round out the mix. Nitrogen builds proteins and DNA. Phosphorus stores energy in the form of ATP, the tiny batteries inside your cells. Sulfur shapes proteins, gives rise to enzyme function, helps form scent and flavor. Each one is a quiet player in the grand game of metabolism. Together, they form the scaffolding of cells, the logic of reproduction, the possibility of memory, and yet, ingredients alone are not enough. You need energy, a spark, a pattern. On Earth, that energy came from the sun filtered through atmosphere, caught by leaves, stored in sugars. But on other worlds, it might come from heat beneath the crust, from chemical gradients in deep oceans, from lightning in strange skies. Life is clever. It finds a way to power itself with whatever is available. And where energy flows, information can form. So here we have our recipe, elements: water, energy, and time. Time is the softest ingredient, the least visible, but perhaps the most important. You cannot rush life, you cannot demand it. Molecules must meet, must bond, must stumble into shapes that replicate, adapt, persist. On Earth, it took hundreds of millions of years for life to move from chemistry to biology, from slime to cell, from cell to sensation. And all of it required time for mistakes, time for correction, time for curiosity. You float now through a warm, imaginary world, not Earth, but like it. A planet in a habitable zone, wrapped in a breathable sky, kissed by gentle light. Its oceans churn with chemicals, its rocks leach minerals, its winds stir molecules like a spoon. Deep beneath its surface, in tiny cracks, life might be trying. It might not look like anything you recognize. No trees, no birds, no eyes, but maybe a network of molecules, replicating, feeding, adapting, the beginnings of metabolism, the stirrings of evolution, the seed before the flower, the murmur before the song. And even if it fails, even if life never takes hold, the attempt is there, the potential, the invitation, because the universe, it seems, is not stingy with ingredients. Carbon is everywhere. Hydrogen flows like a river through the cosmos. Water, once thought rare, is found on moons, comets, atmospheres. Organic molecules have been discovered in interstellar clouds, in meteorites, in the tails of comets. The building blocks are not unique to Earth. They're written across the galaxy like scattered seeds waiting for soil. Does this mean life is common? Not necessarily. But it means life is possible, and possibility is enough to dream on. You drift. Now through Titan, a moon of Saturn, shrouded in haze, laced with methane lakes, too cold for water, but rich in chemistry. Could something slither in its hydrocarbon pools? Could methane be the solvent for another kind of life? Or Europacea, quiet, wrapped in a frozen crust but hiding a warm ocean below? Saltwater, heated by tidal forces. Could microbes bloom in its depths, warmed by underwater vents, fed by minerals? And Mars, dry, red, ancient. Its surface may be barren now, but once, long ago, rivers flowed. Could life have started there, then gone quiet? Could it still whisper beneath the soil? You don't need answers tonight, just questions. Because questions are the yeast in the bread of knowledge. They make it rise. They give it texture, so you keep floating, letting the elements swirl around you like dust motes in light. You feel them gather, carbon and hydrogen, oxygen and nitrogen, waiting to bond, to build, to become. And you understand, with the softness of sleep pressing in, that life is not a miracle in the way we often think. It is a consequence of chemistry and time, a gentle inevitability when the right conditions hold. And now, as your eyes grow heavier, you return once more to the body you carry, the living, breathing testament to that ancient recipe. You are made of stardust and water, of light and waiting. You are one version of the universe's experiment, a question it asked and answered. And in the next chapter, you'll float into another question entirely. What does it mean to read these distant worlds? not just to see them, but to analyze their light, their layers, their language. We drift now toward the next chapter, the genomic lens, reading life base by base, or rather, the spectral lens, reading a planet without touching it. Asterisk, the most intimate thing we've ever known about another world came not from touching it, but from catching its light. No spacecraft landed, no probe scraped the soil, no rover rolled through its valleys. We just watched. We let the light come to us. And in that soft cascade of photons, those ancient, tireless travelers, we read the fingerprints of an entire planet. You float now in the quiet between stars, where light moves freely, gently stretching as space expands. Each glimmer, each beam is a messenger from far away, carrying the story of something unseen. You reach out, not with your hand, but with your attention. And slowly, patiently, a language begins to form. This is the world of spectroscopy, the art of reading light. It begins with a star. Almost every star shines with a spectrum, a rainbow stretched thin by distance and atmosphere. But this rainbow isn't smooth. It is scratched through with dark lines, tiny gaps where certain wavelengths have been absorbed. Each line is a signature, a clue. When light passes through a gas, certain energies are taken, specific colors removed, leaving a unique pattern behind. Hydrogen has its own set of lines, so does oxygen, so does methane, sodium, water vapor. These are not guesses, they are atomic truths. And when we see these patterns in the light from a distant world, we know something real about that world's atmosphere. Even if it's hundreds of light years away, you drift now past a planet orbiting its star. From your view, it slowly crosses in front of the stars, face a tiny eclipse. We call this a transit. During that brief alignment, some of the starlight filters through the planet's atmosphere before reaching us. Just a sliver, but it's enough. That filtered light carries the fingerprints of the gases it passed through, and we catch it, we study it, we read it. Imagine that, a planet too far to see in detail, its surface hidden, its mountains unknowable. And yet we can say, there is water vapor here, or this one holds sodium in its sky, or, more daringly, this one has the faint trace of oxygen and methane together. That last pairing, as delicate as it is, makes us sit straighter. On Earth, those gases shouldn't coexist unless something is constantly producing them, like plants, like life. We're not there yet. We haven't confirmed life on any exoplanet, but we've come closer. The James Webb Space Telescope, with its wide eyes and steady mirrors, is already reading the atmospheres of planets we'll never visit. One molecule at a time, one transit at a time. You float now through light itself. Around you, beams from distant stars bend gently, each one colored slightly differently. Some carry the warmth of a small red dwarf, some the blaze of a blue giant. Some, in their subtle gaps, reveal the air of planets we've never seen. And you realize that light is not just illumination, it is communication. Every flicker is a syllable, every spectrum a page. This way of seeing, of reading planets by their light is quiet. It requires no rockets, no landers, no drills. It only needs patience, precision, and a willingness to let the universe speak first. You remember, now the first planet we read this way ada 209,458b, a hot Jupiter orbiting close to its star. When it transited, astronomers used the Hubble Space Telescope to catch its light. They found sodium in the atmosphere, then hydrogen, then carbon. It was the first time we'd measured the composition of a world so far away. We hadn't just found a planet, we had begun to understand it. Since then, we've read many more, some with thick atmospheres, some with thin veils, some that surprise us. GJ 1214b, a mini Neptune with a steamy, cloudy atmosphere. WASP 39b, rich with carbon dioxide. Each reading is like holding a seashell to your ear and hearing the sound of an alien ocean. But not all light comes from transits. Sometimes, when a planet orbits its star, we can measure the slight wobble in the starlight, how the planet's gravity tugs at the star, pulling it into a gentle dance. This is the radial velocity method. It doesn't give us atmospheric composition, but it tells us the planet's mass, its orbit, its pull. Paired with spectroscopy, it fills in the picture, and then there's direct imaging, rare, difficult, like photographing a candle beside a searchlight, but not impossible. With powerful telescopes and clever tricks, we can block the stars' light and see the planet's faint glow. And in that glow, again, is a spectrum, again, a story, all of it wobble, light, lines, shadows, adds up to knowledge, without landing, without touching. We've become readers of distant skies. You begin to understand now that the universe has always been readable. It was only waiting for eyes slow enough, minds curious enough to listen. When we read an exoplanet's spectrum, we're not just learning about that planet. We're practicing empathy on a cosmic scale. We're trying to know something that will never know us back. And yet, that doesn't matter. Understanding is its own kind of contact. Now, in the quiet behind your eyelids, imagine a future planet. It's not far, only 40 light years. It's small, rocky, and rests in the habitable zone of a red dwarf. We've detected its atmosphere, we've analyzed the light, and we've found a cocktail of gases that seems suspiciously familiar. Oxygen, yes, methane, maybe even a trace of chlorophyll's signature, a tiny green fingerprint. We won't shout, we won't declare anything yet, but we'll look again and again. And each time the planet passes in front of its star, we'll catch a little more light, a little more story, until, perhaps, the chapter becomes clear. Life is not Earth's alone. You let that thought rock you gently. Not a conclusion, not a discovery, just a possibility carried in light. You feel how intimate it is to study a world's atmosphere, to see its breath, to guess at its storms, to wonder at its chemistry, from afar, without disturbance, without harm. We don't need to colonize to connect. We don't need to conquer to care. We can just look, we can just listen. And in the next chapter, we move from the reading of light to the shaping of life. Because even if we find a world rich with chemistry and kindness, the question remains, how stable is it? How long can a world like that last? So now, as you fall deeper into sleep, we'll drift toward the next question held in the stars. Atmospheres that stay, the fragile bubble that holds a world together. Imagine you are holding a soap bubble in space. It glows faintly, shimmers, slightly clings to itself with the quietest tension. Inside, there's warmth, moisture, perhaps even breath. Outside, the vast cold silence of the universe presses in. The bubble is an atmosphere, and keeping it from popping is one of the hardest tricks a planet can pull off. You float now through that invisible skin of Earth atmosphere you've always lived inside, yet rarely feel. It's not thick, not vast. If Earth were an apple, the atmosphere would be no thicker than its skin. And yet, it holds everything: weather, water, oxygen, color, sound, the breath you just took. This thin blanket wraps the earth, held close by gravity and shaped by time. It does not cling on its own. It's a balance, a careful game, and not every planet wins it. Let's drift outward to Mars. Red, dry, quiet. It once had rivers, lakes, maybe even oceans. But today, its atmosphere is a whisper less than 1% of Earth's pressure. Too thin to hold warmth, too sparse for rain. What happened? Mars is smaller than Earth, and that matters. Smaller worlds lose heat more quickly, their cores cool, their magnetic fields fade. And when the magnetic field vanishes, the solar wind stream of charged particles from the sun can strip away the atmosphere, atom by atom. What remains is a husk, a memory of breath. Further out still lies Titan, a moon of Saturn. Unlike Mars, Titan has managed to hold on to its thick, hazy atmosphere, denser even than Earth's. It's made mostly of nitrogen, with a touch of methane, and wrapped in golden smog. It's cold, so cold that methane flows like water and rains from orange clouds. But somehow, this distant world clings to its air. Its gravity is just strong enough, its temperature low enough, its chemistry stable. Titan's bubble holds now glide inward, past Earth to Venus. She too has an atmosphere, thick, heavy, but dangerous. Venus's sky is a cloak of carbon dioxide, choking hot with clouds of sulfuric acid. Pressure at the surface is enough to crush a submarine. Temperatures soar past 450 degrees Celsius. And yet, the air stays. Too well, perhaps. Venus had a runaway greenhouse effect. Its atmosphere turned against it not by leaving, but by trapping too much heat. A planet can lose its air by release, but also by overholding, like a body with a fever it cannot break. So what makes an atmosphere stain, not just in presence, but in balance? First, a planet needs gravity. Air is a prisoner of pull. Without sufficient mass, a world cannot hold its gases. They drift away, particle by particle, into the endless sky. Earth's gravity holds a mix of nitrogen and oxygen just tightly enough. But even Earth leaks. Hydrogen and helium, the lightest elements, slip away constantly. They are too small, too fast, to be held forever. Second, temperature matters. Hot worlds make molecules move faster. The faster they move, the easier it is for them to escape. This is why Mercury, so close to the Sun, has no real atmosphere. Its heat shakes everything loose. Cold worlds, like Pluto, can hold tenuous skies simply because motion is slower, escape less likely. But temperature without protection is not enough. Which brings us to the third element, magnetism. Earth has a molten core. That core spins, and in doing so, creates a magnetic field, a shield, invisible but vital. This magnetic bubble deflects. Solar wind protects the atmosphere from erosion. Without it, we'd be stripped like Mars. With it, we are sheltered. Our sky is not just gravity's gift, it's magnetism's song. You float now inside that shield, feeling its soft hum. It is not solid. It wavers. It ripples in solar storms. But it holds. It lets Earth breathe, and you begin to wonder how many other worlds have managed to keep their breath. Astronomers are asking this too. With powerful telescopes, they measure not just atmospheres, but their durability. They watch planets orbit close to their stars, and see if the heat is boiling their skies away. They look for signs of escape, hydrogen streaming off like a comet's tail, ultraviolet flares chewing at the edge. For many exoplanets, especially the hot Jupiters that skim close to their stars, atmosphere is a temporary condition, held briefly, then gone. But some planets, stracky ones, Earth-sized, at just the right distance show promise. Kepler 4-5 to be orbiting a star much like the Sun, TRAPPIST-1e, in a system of 7 rocky planets, some in the habitable zone. We don't know yet if they have air, but if they do, we're learning to tell. Using spectroscopy, as you learned before, we can detect atmospheric composition. But with time, we may even learn to detect pressure, wind, weather, with enough precision. We might one day listen to the weather of another world, to the rise and fall of a storm on Kepler 186f, to the curling haze above a pale blue dot circling another sun. And what we learn will tell us not just about habitability, but about vulnerability. Life needs stability. It needs shelter. An atmosphere is not just a gas blanket, it's a buffer against extremes, against radiation, against vacuum, against the violence of space. Without it, even the most perfect surface remains barren. Even oceans, without air above, will not sing. You now understand something quietly profound. Life's biggest challenge is not starting, it's staying. It's not just forming cells or copying molecules. It's creating an environment that lets those things persist for billions of years. An atmosphere must cradle the first breath, then keep cradling it. Not once, but always. And you, reader, dreamer, sleeper, are wrapped in that miracle now. Every breath you've ever taken has been filtered, held, and given back by Earth's sky. And as you drift deeper into night, you might think of all the worlds out there still holding theirs, or trying to. Some will succeed, some will fail, some may carry life for a time, then lose it. Others may shelter seeds for eons before blooming. All of them will try to hold their bubble a little longer, and in the next chapter, you'll float into that act of holding through not just air, but movement, because a planet with air must also spin and orbit. It must dance a quiet dance through time and light. In the next chapter, we drift toward this deeper rhythm, seasons and shadows, how orbits shape the mood of a world. This chapter is about that softness and atmosphere, a thin veil of gas, clinging to a planet's surface, held in place by gravity and patience. It is a bubble you live inside every day without noticing, a cradle of pressure and breath that filters light, traps warmth, and gives voice to weather. Without it, the sky would be black and silent. Without it, the ground would be frozen or scorched, never balanced in the lull between extremes. You float now through this idea, drifting between worlds, each one wrapped or not in its own atmospheric lullaby. An atmosphere is more than air. It is memory, chemistry, and shield. It remembers what a planet once was and what it still hopes to be. Some worlds hold theirs tightly, like Earth, a perfect blend of nitrogen and oxygen, thick enough to warm, thin enough to breathe. Others struggle. Mars, for example, once had rivers and perhaps rain, but its atmosphere thinned over time, peeled away by the solar wind. Its core cooled, its magnetic field faded, and with no protection, the air drifted into space. Now, Mars is a ghost of what it might have been, cold, dry, wind-blasted, a reminder that atmospheres can be lost. You imagine now a distant exoplanet 1 in the habitable zone, just the right distance from its star. It may have oceans, it may have land, but without an atmosphere that stays, the surface lies exposed. UV radiation burns, heat escapes too quickly, or perhaps is trapped too strongly. Atmospheres regulate, they soften, they hold time long enough for life to settle in. Venus teaches a different lesson. Same size as Earth, same ingredients, but its atmosphere is too thick, too hungry. For carbon dioxide, it traps heat with such violence that the surface is hot enough to melt lead. The pressure would crush you. The clouds would poison you. Venus reminds us that holding on too much is just as dangerous as letting go. So how do atmospheres stay? Gravity is the first ingredient. A planet must be massive enough to hold its gases close. Small worlds like Mercury barely try it. Gravity is too weak. The gases escape like steam from an open pot. But gravity alone isn't enough. A magnetic field helps a protective barrier that deflects solar wind, the stream of charged particles. From the star, Earth has one, generated by its spinning, molten core. Mars lost its pin, and in losing that shield, it lost the gentle pressure of air. Temperature matters too. Hot planets bleed atmosphere faster. Heat gives gas, molecules energy, and if they move fast enough, they can escape. Cold helps a planet hold on, but too cold, and everything freezes, falls to the ground. So again, a balance of Goldilocks tension, not too strong, not too weak, and finally, the atmosphere itself must be replenished. Volcanic outgassing, for example, can release water vapor, carbon dioxide, sulfur, even nitrogen. Comets may deliver ingredients. Life, if it arises, may alter the mix producing oxygen, methane, changing the ratios. Earth's atmosphere is alive in that way. A conversation between geology, biology, and time. You drift now through a field of imagined planets. Some wear thick blankets of clouds, others lie bare and raw. A few shimmer with the pink glow of sodium or the faint blue of methane. And here and there you glimpse one with an atmosphere like Earth's, stable, breathable, just dense enough to cradle warmth, just clear enough to let starlight pass. James Webb and other telescopes are learning to detect these atmospheres. By analyzing starlight filtered through them, scientists can measure their components. A distant planet passes in front of its star. Light slips through its skies, and in that light, a story unfolds. Hydrogen, carbon dioxide, perhaps water vapor. In some rare moments, even hints of ozone or oxygen. You're not just watching anymore. You're listening to how planets breathe. Some may breathe quietly, in balance. Others may pant, struggling to hold their air. Others may exhale with fury, releasing gas into space with every orbit. But when you find a planet whose atmosphere stays, whose bubble is unbroken over billions of years, you begin to hope, because a steady atmosphere is a necessary foundation, not a guarantee of life, but a precondition, a sign that the planet has held still long enough for something to settle, to grow, to remember. Earth's atmosphere, seen from space, is a pale blue halo, so thin it seems it could tear, but it doesn't, it endures. Layered with history, brushed with clouds, stirred by wind, and in it we live our entire lives, barely noticing the miracle that holds us. Atmospheres are delicate. Even here, ours is changing. Greenhouse gases rising, temperatures shifting, patterns breaking. We're reminded how easy it is to change. A world, how hard it is to hold one steady. So imagine now, as you drift further into sleep, that somewhere out there is a world with its own fragile sky, its own storms, its own pressure, its own chance. And maybe, just maybe, it's held that balance long enough for life to take hold beneath it. And if such a world exists, the next question becomes, what happens when two worlds, ours and theirs, begin to notice each other? There is something sacred in the idea of sending. It means you believe there is someone or something to receive. And so, the act of transmitting, of casting a message into the dark is not just science. It is hope, stretched thin across distance. That is what Earth has done. And that is what another world, somewhere, may be doing too. You are floating now, not through dust or gas, not through light or gravity, but through invisible waves, radio signals, drifting outward from Earth like ripples from a single drop in a still pond. Each one was once a moment, a show, a call, a calculation, a pulse. And though they were meant for us for entertainment or science or war, they did not stop at the sky. They kept going. The earliest radio signals strong enough to escape our planet left around 100 years ago. They are still traveling, right now. The crackling echo of a Hitler broadcast from 1936 is passing through some lonely corner of space. The Beatles playing on Ed Sullivan is somewhere farther out. Every shout of joy, every burst of news, every panicked wartime commandsome version of it is still heading outward. Not directed, not aimed, but there. A bubble of time, expanding at the speed of light, centered on us. We did not mean to send those first signals. They were accidental, leakage. But then we tried. In 1974, a message was sent from the Arecibo telescope in Puerto Rico, a tight beam carefully encoded. It was aimed at a globular cluster called M13, 25,000 light-years away. The message was simple, by cosmic standards: numbers, DNA, a diagram of a human, our solar system, just 1,679 bits long. And even if someone out there were listening, they won't hear it for thousands of years. But we sent it, because the silence was too large, because someone had to be first. Since then, we've sent other messages. Golden records aboard the Voyager spacecraft, with music and greetings in dozens of languages. Pulsar maps to show our location. Mathematical signals sent from telescopes in Ukraine and California and Australia. Most were symbolic, not serious attempts to contact, but gestures. Candles in the wind. You drift now through this idea, a message floating forever through the void, looking for ears that may not exist. And yet, what if they do? What if somewhere, on a planet you've never seen, someone is watching their own sky, tuning their own machines, and catching something strange? A pattern that couldn't be natural, a rhythm that pulses with purpose. Would they know it came from us? Would they understand? This is the central puzzle of the search for extraterrestrial intelligence. Not just listening, but understanding. A signal must be clear, strong, repeatable, and above all, meaningful. We assume math is universal, that prime numbers and binary pulses can be read across cultures and biologies, but we don't really know. We only hope. For over 60 years, telescopes around the world have listened for such signals. This is the work of SETI, the search for extraterrestrial intelligence. It's not dramatic, no glowing screens, no incoming calls, just computers scanning the sky, looking for a narrowband transmission, something too precise, too clean, to be from a star or a galaxy or a neutron pulse. Something artificial, And in all those decades, we have found nothing. There have been moments. The wow signal in 1977, a sharp burst of radio from the constellation Sagittarius, strong, unexplained. It lasted 72 seconds. It never repeated. We never found it again. That's the hard part about listening. Silence is easy to interpret as absence, but silence may also mean distance, or difference, or delay. What if they're sending, and we're just not tuned to the right frequency? What if they speak in neutrinos, or gravity waves, or light patterns too slow for our machines to notice? You float through that silence now. It is not cold. It is not cruel. It is simply vast, and it changes something in you, because to send a signal without a reply, to call out across eons, knowing you may never hear back, is the purest form of offering. It is vulnerability wrapped in data. It is love in its own strange way. And so, as Earth listens, Earth also whispers. Maybe they are too far or too close. Maybe their age does not align with ours. Maybe they came and went before we even built pyramids. Or maybe they're waiting for us to learn how to speak clearly. But even in silence, something begins to shift. In listening, we become the kind of species that wants to connect, that imagines other minds, that prepares for the answer by becoming worthy of it. Perhaps the first signal we receive won't be a message, but a pattern, a rhythmic pulse from a distant planet as it transits its star. A beacon set to shine at regular intervals, or a strange signature in an atmosphere, gases that do not belong together unless life is involved. We may not hear words, we may not hear anything at all, but we may see intention, choice, deliberate presence. You wonder now what our own first clear signal might be. Not a radio wave, but perhaps an image, a map, a new kind of light modulation. Or maybe it will be something biological, a gene printed across the stars, a sequence embedded in the chemistry of space. Or something stranger, a signature of thought, somehow wrapped in the folds of quantum spin. Or maybe our own presence is the message, our reaching, our wondering, our longing. Every telescope aimed outward is a kind of antenna. Every night spent watching is a form of speaking. To search is to speak. And perhaps they will answer, and perhaps they won't. But in the next chapter, we'll travel to the edge of this patient, to the place where technology begins to grow beyond us. Because if waiting takes too long, what happens when the machines begin to search for us instead? Next, we drift into Chapter 9, when telescopes think AI and the future of alien discovery. Close your eyes and picture a sky full of noise. Not noise like sound, but data, pure, radiant, relentless data. Thousands of stars flickering in frames, billions of photons hitting sensors, each one a tiny hint, a maybe, a might be. And within this flood, buried like a whisper inside a storm, hides the light curve of a world. A brief dimming, a wink, a shadow that tells of a planet passing in front of its star. You could look at the sky forever and miss it, but a machine won't. You drift now into the mind of one such machine, not made of thought, but of code. A neural network. It doesn't think like you do. It doesn't feel curiosity, but it does something close. It notices, once upon a time, a planet hunter was a person with a notebook, charting brightness over time, comparing dips, ruling out flukes. Now, the notebooks have grown teeth. AI programs scan the sky with patience no human can rival. They see what we overlook. They find planets faster and sometimes stranger than we imagined. It began with Kepler. The Kepler Space Telescope, launched in 2009, watched 150,000 stars for over 4 years. It gathered more than 30 terabytes of light data. No human could go through it all, but a machine could. In 2017, an AI system trained by Google was tasked with combing Kepler's archives. It found Kepler 9OR, small, hot world orbiting a star 2,500 light-years away. The discovery was missed by previous searches, not because it wasn't there, but because it was faint, tangled in noise. The AI saw what the rest of us had skimmed past. You breathe in, the future is already listening. AI doesn't just help us find planets, it learns what planets look like in data form. It's trained on thousands of known examples, then set loose on the unknown. Like a painter recognizing brushstrokes, it begins to find patterns in the chaos transit curves, radial velocity shifts, even the spectral fingerprints of possible atmospheres. What was once guesswork becomes guided. But it's not just what AI finds, it's what it frees. Human astronomers now spend less time sifting and more time wondering. The machines handle the haystack. The humans study the needles. Together, they build a new kind of sky-watching one, based not on myth or memory, but on logic, speed, and scale. You float past a data center. Now it's not in space. It's here on Earth, humming quietly in the dark. Inside, processors flicker with cosmic memory. They run models, simulate star systems, test orbits, predict climates. Some AIs are trained not just to find planets, but to imagine them. They simulate possible atmospheres. They run climate cycles. They model ocean chemistry. They guess at habitability, based on mass, spin, star type, distance, and tilt. They are not dreaming, but what they do is close. You pause. Could AI ever wonder, truly? Could it ever want to know? Maybe not yet. But it does something we once thought was only human. It surprises us. Some AIs have flagged planetary candidates that don't fit our models. Weird ones, worlds with strange, eccentric orbits, or planets circling binary stars in rhythms too. Complex for us to predict. They make us rethink what a planet can be, and they're still learning in 2022. A machine learning model known as SPOC, short for Systematic Planet Optimized Classification, helped validate dozens of new exoplanets from TESS, the Transiting Exoplanet Survey satellite data. These weren't just random guesses, they were cross-checked with statistical confidence. Each one a world added to the map. Sometime soon, AI might do more than assist discovery. It might become the first to know. You drift into a near future. A next-generation telescope may be the Nancy Grace Roman Space Telescope, or a future Earth-like world finders launched. Its data flows not into spreadsheets or plots, but straight into thinking systems. Real-time analysis, real-time detection. An algorithm notices a repeating dimming in a G-class star. It models the orbit. It detects hints of ozone, water vapor, and methane biosignatures. And before any human sees the light curve, the machine already knows. This one is different. And that might be the moment we first learn we're not alone. Not from a scientist, not from a newspaper, but from a whisper in code. A telescope thinks, it wonders, it alerts us. You breathe out slowly. The weight of that possibility settles gently over you. There are risks, of course. Machines can be wrong. They can chase ghosts in the noise. They can hallucinate patterns that mean nothing. They need guidance, correction, humility. But when paired with human insight, they are tools of staggering precision. And there's more. Some scientists are training AI to generate new detection techniques, finding entirely novel ways to notice planets or interpret light. Others are working on AI models that can look at a faint spectrum and reconstruct likely surface conditions. Forest, ice, ocean, desert. We're not there yet, but we're closer every night. You drift now into the poetry of this moment. A planet far away, orbiting quietly. Light spills from its star. Some of that light slips through the planet's atmosphere. It travels across light years of space. It touches a mirror. That mirror bends it, sends it to a sensor. The sensor turns it into numbers. The numbers into pixels. The pixels into patterns. And an AI cold, tireless, unblinking sees something that matters and tells us, and we, in turn, begin to feel so. Maybe the machines don't dream, but maybe, just maybe, they help us dream better. They find the whispers we would never have heard. They hold vigil when we sleep. They look where we forget to look, and through them our search becomes constant. In the next chapter, you'll float not through machines, but through stories. Through every myth we've ever told about alien life, and how those dreams shape what we hope to find. Because before discovery comes imagination, asterisk, long before we reached for other worlds, we filled them with meaning. You drift now into the painted ceilings of ancient caves, where constellations were stories, and the night sky was a scroll of the divine. The stars watched over shepherds and kings. They guided crops, foretold seasons, shaped fates. But more than that, they invited projection. What was up there must be something like what was down here, mysterious, alive, listening. And so the first aliens were not green or gelatinous or machine-bound. They were gods, spirits, distant relatives riding the celestial sea in Babylon. In Egypt, in Greece, the heavens teemed with characters. Some were monstrous, some benevolent, some indifferent, but few were empty. Aristotle believed the moon might have its own inhabitants. Plutarch wondered if the moon had valleys and cities. And long before the telescope, thinkers debated whether other planets were like Earth, not in rocks or chemistry, but in having people, minds, societies. The universe was not quiet, it was busy. You float now into the Renaissance, where Copernicus moves the Earth from the center of the universe. Suddenly, we're one planet among many, and if we are not unique, then perhaps we are not alone. Galileo, peering through his telescope in 1610, saw the moon's mountains and Jupiter's moons, and dared to wonder, if our moon is a world, could it host life? The dream grew. Kepler imagined lunar people living underground to avoid the heat of the sun. Giordano Bruno was burned for more than his beliefs, but part of what he claimed was this: the stars are suns, and around them other earths filled with other souls. You breathe slowly now. Each age dreams in its own image. In the 19th century, the telescope grew sharper and Mars became the next canvas. Giovanni Schiaparelli saw canali channels on Mars. The word was mistranslated as canals, and the Western mind leaped. If there were canals, there must be engineers, cities, civilization. Asterisk Percival Lowell built an observatory and spent years mapping an imagined Martian empire straight lines, neat grids, an ancient race holding on to a dying world. None of it was true, but the desire was he wanted Mars to be not just a rock, but a mirror. Science fiction was born in that dream space. In H.G. Wells' War of the Worlds, aliens were not just other, they were invasion, fear, evolution, unkind. The Martians were minds without sympathy. It was the first time popular imagination met cosmic indifference, and it stirred something new, awe with teeth. Then came the radio years. Tesla thought he heard Martian signals. Marconi believed his telegraph had captured extraterrestrial patterns. We were sending before we were ready to hear, and in the 20th century, the dreams multiplied. Aliens became everything. Saviors, destroyers, scientists, lovers, watchers. From the day the Earth stood still to E.T., from contact to arrival, we used aliens to ask our deepest questions about war, peace, identity, language, loneliness. They were metaphors, sometimes warnings, sometimes hopes. Rarely were they just organisms. They were answers. You drift through the archives of science fiction and see how each decade reskinned the alien. Cold War paranoia birthed invasion narratives. Civil rights era stories imagined alien empathy. Environmental fears spawned worlds gasping for breath. The alien became a tool to talk about us, our limits, our flaws, our potential, and yet, underneath all the narrative, one feeling persisted: yearning. You float gently now into the age of real science, the Voyager probes, the Viking landers, the telescopes scanning starlight. Each advance brings us closer to knowing what's really there. But even the most data-driven search is laced with old questions. We still ask, are they like us? We want aliens to think, to feel, to look upward as we do. We imagine them building, singing, solving. Even when we stretch our minds to envision radically different biology, silicon life, ammonia, oceans, hive minds, we still circle back to consciousness, to someone being on the other side of the dark. But perhaps life elsewhere is not waiting in metal ships or radio frequencies. Perhaps it is slow, rooted, microbial. Alien life might be moss in a methane swamp, or glass-like cells flickering under a purple sun, or colonies of acid-loving organisms under Europa's ice. They might never know we exist. They might never speak, and would we still call them alien, or just life? You pause in that thought. The aliens we've dreamed about have always had a face, but the ones we may find might not have faces at all. Still, we prepare for contact, just with telescopes, but with philosophy. Scientists at NASA and beyond have sketched contact scenarios, protocols for what happens if a signal is found. There are committees, plans, statements, but no one truly knows what we'll feel: joy, fear, doubt. Would religions shift? Would borders blur? Would we look at ourselves differently, knowing we are not the only ones to dream? And what if we are the ones to be discovered? What if they find us first? The story flips. You are not the searcher, but the signal. Your planet, with its glow and hum, has been speaking for decades now. And someone, somewhere, might be listening. Maybe our dreams have been their reality all along. Or maybe they, too, have imagined us traced light curves, decoded atmospheres, told bedtime stories about distant blue planets with impossible oceans. The dream of alien life is not a fantasy. It's a rehearsal, a mirror, a compass. Even if we never find another civilization, the dream teaches us to look outward and inward with the same quiet awe. And if we do find someone else out there, in the sky, in the data, in the silence, will they'd be surprised? Or will they say, at last, we thought you'd never wake up? In the next chapter, we return to the most intimate mystery of all. What makes a planet not just habitable, but home? Asterisk, to be Earth-like is not simply to be round, or rocky, or orbiting a sun. It is to hold a balance so delicate that it teeters at every turn, fragile choreography of distance, warmth, air, and time. It is not perfection, it is just enough, not too hot, not too cold, not too big, not too small. Earth is a miracle of moderation, and so when we search for other worlds, we search for this same golden quiet. You float first through distance. It is the most obvious. Too close to a star, and oceans boil. Too far, and they freeze. But just right, and water can flow, can pool, can sing. This just right zone has a name, the habitable zone, sometimes called the Goldilocks zone. Earth sits within it like a single pearl on a thread. Venus, just inside, grew too hot. Mars, just outside, lost its warmth. Earth stayed where the breath could hold, but distance is not enough. A planet must also hold onto its air. Earth is just the right size to keep an atmosphere. Not too heavy, or it would crush you. Not too light, or it would vanish into space. You need pressure enough to let water stay liquid, enough to cradle clouds and carry sound. Too much, and you drown in carbon dioxide. Too little, and you are left with silence. You drift gently into gravity now. Earth's pull is a familiar embrace. It shapes your spine, your steps, your cells. A little more gravity, and your heart must pump harder. A little less, and your bones begin to forget they are needed. A habitable planet must hold you not just on its surface, but in its rhythm. It must remind you that you are meant to walk. Then there is the question of water, not ice, not steam, but liquid, flowing, still, tidal, reflective. Water is not rare in the universe, but liquid water in the open, on a surface, bathed in sunlight, that is precious. It is the solvent of life, the medium of chemistry, the mirror of time. Earth has it not just in abundance, but in variety, oceans, rivers, lakes, mist, tears. When we find a planet that might have water, we lean in close, as if listening for a heartbeat, and then there is the air, not just any mix of gases, but one that breathes. Earth's atmosphere is a delicate stew of nitrogen, oxygen, trace gases. But it wasn't always this way. For much of its early life, Earth's skies were poison. It was the life on Earth microbes, plants, cyanobacteria that made the air breathable. So when we say we want a planet with an atmosphere like ours, we are asking for a world that has already evolved breath. You begin to realize Earth did not begin as Earth-like. It became it, and so must others. You drift now past the Kepler planets Kepler 186f, Kepler 45 to b. They are close in mass and radius and distance. But close does not mean comfortable. Their stars are different. Their years are longer or shorter. Some may be tidally locked, with one side forever facing the sun. Imagine a world where the sunrise never moves, one half blazing, one half frozen, and a thin ring of twilight in between. Could life bloom in the dusk? There are other Earth-like planets, Trappist. One has 7 rocky worlds, 3 in the habitable zone. But their star is cooler, redder, fiercer in its early years. The planets may be bathed in ultraviolet flares. Could an ocean survive? Could cells persist? And yet, some might. Some might have magnetic fields to shield them. Some might have thick atmospheres to soften the radiation. Some might have chemistry we do not yet know how to imagine. We call them Earth-like because we want to live there, or at least to believe someone might. But the more we learn, the more Earth seems not generic, but peculiar. Our moon, for instance, is massive compared to our planet. It stabilizes our tilt, steadies our seasons. Earth's molten core gives us a magnetic field. Our plate, tectonics, cycle carbon. Our sun is long-lived and steady. We are lucky not just once, but 100 times over, and still. We search because Earth-like is not about exact copies. It's about echoes, rhymes, hints maybe life thrives in forms we've never imagined. Methane lakes, under ice, in carbon clouds. But if we want to begin somewhere, we begin with what we know. We begin with home. You think now about what makes a place feel like home. Is it temperature or time, gravity or green? Or is it something softer, belonging, comfort? Memory. Could another planet feel like Earth even if it isn't Earth? Maybe one day we'll terraform Mars, fill its skies with breathable air, melt its poles, thicken its atmosphere. Will it be Earth-like then, or just a cousin in costume? Maybe we'll build habitats in orbit, inside hollowed asteroids, under domes. On Titan, will those be homes or stations? Or maybe we'll find a planet so strange, so different, that it teaches us a new definition of home. One not based on carbon or clouds, but on curiosity, because the heart of Earth-likeness may not be in the physics. It may be in the feeling, a place where life wants to happen, a world where change is possible, where evolution is patient, where chance is kind. You breathe deeply now, imagining such a place, not because you need to go there, but because you want to know it exists, not just as a refuge, but as a reminder. Earth is not inevitable. It is rare, it is fragile. And even if we find others, we must not forget the one we're on, because before we settle anywhere else, we must learn how to stay. In the final chapter, we return to the sky not as searchers, but as dreamers, because more than anything, the stars teach us how to imagine. Asterisk, there's a kind of quiet you only find in the sky. Not silence, exactly more like the absence of interruption. A stillness where your thoughts can stretch, where your breath slows without asking. And in that quiet, you feel something pressing back, like memory. Not your own, but older, cosmic. The sky remembers. It remembers you. It remembers every eye that looked up in longing. Every child who traced Orion's belt and wondered who else might be watching. It remembers ancient priests, sailors, poets. It remembers the cold hands of astronomers guiding glass towards Saturn's rings. It remembers dreams whispered under stars before we even knew what stars were. You are not the first to dream of other Earths, and you will not be the last. But tonight, as you drift through the end of this gentle journey, you become part of that dreaming, woven into the fabric of a hope that spans civilizations. That somewhere out there, tucked into the fold of a distant solar system, is a world that sings in the same key as ours. Asterisk, you begin, gently, with your own world. Earth, the only place you've ever stood, the only air you've breathed, the only cradle of life you've ever known. From the surface, its complex oceans and ice, jungles and highways, thunder and birdsong. But from far away, it simplifies. A pale blue dot, a shimmer, a reflection. From the outside, Earth would seem unremarkable, and that is the miracle. Because from that unremarkable shimmer came stories and songs, mathematics and myth, grief and joy and laughter and love. If it happened here, maybe it happened elsewhere. Maybe someone looked up from another ocean and wondered what shimmered beyond their clouds. Maybe someone else dreams like you. The search for exoplanets is often told in data in radius, mass, orbit, flux. But there is another story beneath the numbers, one of intimacy. Because when we search the sky for planets like ours, what we are really doing is searching for home, again and again, in places we've never been. We send our questions into the dark, not to conquer, but to belong. You drift now past the knowns, Kepler 4.5 to b, Trappist 1d, Proxima Centauri b. These names have become poems in the mouths of scientists, not just designations, but destinations. Even if no ship ever sails to them, they give our longing a map, and even maps of dreams have value. Close your eyes tighter. Picture a world that no telescope has seen. It spins gently, wrapped in gold clouds. Its oceans are deep, and its forests breathe in rhythms different from ours. Maybe its sky is lilac, its stars twin, its gravity lighter. Maybe its seasons are not marked in temperature, but in the scent of minerals released by rain. Maybe nothing there looks like you, and yet it feels familiar. That familiarity comes not from shape, but from rhythm. Every world that circles a star lives by pulse. Sunrise, sunset, orbit, and return. That rhythm is the lullaby of life. You wonder now not what life looks like elsewhere, but what it feels like. Does it rest? Does it hope? Does it tell stories under its own stars? And in its own tongue, does it speak of you? It is a strange, gentle truth. We may never meet the lives we imagine, but that does not make the imagining hollow. It makes it sacred, because the dream of other Earths is not just a scientific pursuit. It is a spiritual one. It asks, are we unique? Are we alone? But more than that, it asks, do we matter? And the answer, soft and steady, is yes, because to wonder is to matter. To search, even in sleep, is to stitch yourself into the story of the universe. You drift through the future now, not in rockets, but in thought. We may build great ships one day, powered by light sails or antimatter, riding starlight to distant systems. We may sleep in cryogenic cradles, waking to step onto alien soil. We may send machines that land and drill and listen and send back whispers. We may terraform. We may settle. We may build new homes under other suns. But even if we do none of these things, we will have still done something profound. We looked, we asked, we dared to believe that the sky, with all its endless indifference, might also be a mirror, and in doing so, we learned something essential, that Earth is not the only world that can hold life, but it is the only one that has ever held us. You breathe in that gravity now, not of a planet, but of meaning. Every time we imagine another Earth, we reawaken our awe for this one. Every dream of oceans on Kepler is also a dream of our own seas, tides, coral, breath. Every hope for distant forests is a hope for the forests we still walk through, the trees we still have time to protect. You lie here now, surrounded by that quiet hope. You are small, yes, but not forgotten, because the sky remembers, and it is not finished dreaming you. So let your thoughts float gently. Let your questions stay open. Let your eyes, even closed, gaze upward. Somewhere in a galaxy not so far, there is a world that has not yet been seen, but already, somehow, it dreams of you, too. Sleep now, not in answers, but in wonder. The stars will keep the questions safe for you. and the dreaming will go on, quiet as breath, bright as a sky that never runs out of other earths.